channel. Today I'm going to be showing you guys about my math fair presentation. My math fair presentation is called The Math Behind the Cube. Get it? I decided to do the math fair presentation on Rubik's Cubes because so many people in my class had Rubik's Cubes, and I remember that I had one, but I never learned how to solve it, and I thought it would be cool if I did. So to learn how to solve the cube, I learned about the structure of the cube and the cube notations, because that helps you learn about how to solve it. And out of curiosity, I thought it would be cool if I learned how mathematical concepts apply to cubing. And lastly, I also decided to do this on the Rubik's Cube because I wanted to compare myself to the top 5 fastest cubers and my classmates. The first section of my presentation is speed cubing. So speed cubing is basically like a group of people who are really fast at solving a cube and who do competitions to see who's faster. So in this first graph here, this is about the progress of my class, me, and my dad. The colors represent all the people, and these are the times on the left. And at the bottom, we have the different dates. You might be wondering why most people are starting right here, but other people are starting there. The red one's me, and the green one's my dad. And we didn't know how to solve the cube at that time, so only my classmates did. In this graph, you should be able to see a little bit of progress about us doing a little bit better. I was timing them for 2 weeks, maybe a little bit more. And this is the data that I got. Don't worry, there's some more. If you thought it was too little, we have a little bit more there. This is just a little bit bigger than my presentation, that's all. Yeah. So that's the data. Here you go. You can pull that up. Okay, so the graph below it shows our top 5 fastest solves. So the colors represent our different trials, 1 through 5. These are the times and the names. I decided to calculate our averages. To do that, I just turned the minutes into seconds and added all the seconds together. Then I divided it by 5 because that's how many trials we have. And then I turned it back into minutes and seconds. The fastest average goes to Weston. He got 43 seconds as his average. Second place goes to Everett, who got 1 minute and 5 seconds. And third place goes to me, who got 1 minute and 28 seconds. On the graph below it, it looks pretty similar. It's a very similar setup to this, but these are the top 5 fastest solvers, speed cubers. And I like the graph above it. The colors represent the trials, and on the side, on the left, we have the times, and at the bottom we have the names. I also calculated their average, and on the WCA championship, the fastest average or fastest time was 4.6 seconds, and Ji Hang Wang was the one who got it. Now, the second part of my presentation is about the mathematics behind the cube. Let's start with some basics though. So I have a diagram here of the cube, and I also just wanted to say that there are 6 faces, 8 corner pieces, 1, 2, 3, 4, 5, 6, 7, 8. 6 center pieces, 1, 2, 3, 4, 5, 6. And 12 edge pieces, these pieces here. I'm not going to count all of them. And I also just wanted to say that orange always opposites the red, green always opposites the blue, and yellow always opposites the white. Now let's look at cube notations. So R means turn the right side clockwise. So this is R, so this is the right side and clockwise. L means turn left side clockwise. B turns back side clockwise. D means down, F means front, and U means upper. If you ever see any of these notations, that's why it has an X, because any of these notations with a little number next to it means perform the move the number of times. For example, if we were to do R3, 1, 2, and 3. Then, if you ever see any notation with a little I next to it, that means turn the notation counterclockwise. For example, we could do F inverted, so we would turn it counterclockwise like that. There are things called algorithms. Algorithms are a set of notations in order that help you solve the cube. Now, let's see how the mathematical concepts apply to cubing. So, commutative property is basically a law that states that no matter the order of factors, the number will stay the same. For example, 1 times 2 equals 2 times 1. It equals the same thing because 1 times 2 equals 2 and 2 times 1 also equals 2. So the order doesn't matter. Now let's try to apply this to cubing. Well, if we were to do F and R, so F and R, would that equal the same thing as R and F? As you can see, the cubes aren't facing the exact same direction. That's because the order actually does matter in these things. So they don't equal the same thing. So the commutative property in multiplication doesn't apply to cubing because the order does matter in cubing. Now let's look at the identity property in multiplication. So it's basically like another law that states that any number times its inverse equals 1 whole. So why don't we begin with 4? If we turn 4 into a fraction, that would be 4 over 1. And to find out its inverse, we basically just need to flip the fraction over. So 4 over 1, if you flip it over, it's 1 over 4. And it equals 1. I was kind of surprised by that at first because, if we were to do 4 times 2, what would that equal? That would equal 8. That's more than 4, right? But here, we're getting a number less than 1. We're getting a number less than 4, which is 1. So how does that work? Well, that's because we're multiplying fractions. So if we multiply the denominators, which is 1 times 4, that equals 4, and then the numerators, that's 4 times 1, that also equals 4, and then that equals 4 over 4, which also equals 1. Now let's see if we can apply this to cubing. So if we were to do R and followed by R inverted, that equals 1 whole. We call the state that the cube is in 1 whole because that's how it is. And then when we change it a little bit to turn it back into the 1 whole that we were at, we just have to undo it by doing its inverse. So any notation times its inverse equals 1 whole. So the identity property does actually apply. So what would happen if we added both of them together, commutative property and identity property? Well, so let's begin with a mini algorithm. So F and R, how would we undo that? Well, you would think, oh, simple. You would just do F inverted and then R inverted, right? But as you can see, that's not true because it's in the wrong order. So how would we invert it? Or undo it? Well, if we look at commutative property, we learned that that doesn't apply. Why? Well, because the order does matter actually. So what we have to do is we have to reverse this order and then we can invert it. So if we reverse the order, so we would start with R inverted and then F inverted. Well, to put this simply, you put on your sock and then your shoe, and to take it off, you take off your shoe and then your sock. So I wanted to also share with you some fun facts about the cube. So the Rubik's Cube was invented by Rubik. The centerpieces of a cube don't really move. It was originally named the Magic Cube, not the Rubik's Cube. The fastest solve was 3.13 seconds, and you can scramble it in 43 quintillion different ways. Here, let me show you. It's a big number. That number right here, but don't worry, it still goes on. It goes up to right there. These two lines, which are actually a lot of ways. And you might be wondering what this logo is. Well, as we already know, the logo of the Rubik's Cube is, well, this. But this cube right here actually has magnets inside of it that make it a lot easier for you to turn. And it's called the GAN cube. And that's the one that the professionals, these guys right here, use. And I also wanted to show you how I solved I wanted to show you me solving the cube. So let's get started. Enjoyed my presentation, and I also hope that you learned at least a little bit about cubing and how the Rubik's Cube works. And don't forget to subscribe, give a big thumbs up, and click the notification bell down below so you get notified when new videos come up. Bye!